Boom. Hello and welcome to Calculus 1. What is calculus? Why study calculus? Can we skip calculus? Can you skim through calculus and not pay attention? Why is it part of all STEM majors and some of the business majors and all that? Well, because calculus is a study of a change, and things in life change, right? So calculus, or as I say with K's, calculus, because it should be calculus, is a study of change. Your body weight changes on a daily basis. You are the lightest when you wake up in the morning, and as the day goes on, you have your meals, you become heavier and heavier and heavier. You are tallest for the day when you wake up in the morning, because your joints and everything stretched in your sleep. And then, when you get up and you become vertical, your upper body weight compresses your joints ever so slightly, so you go to bed shorter than when you wake up. You sit in your car and drive from point A to point B, being that we are still driving the gas-powered car because we are a pathetic species. The weight of the entire system as you burn the fuel and your energy, the weight of the entire car system goes down as you're going from point A to point B. So systems change. Now we can find a lot of other stuff. You can figure out that the volume changes with the added temperature, and change the pressure, volume can change. There are a lot of different things that you can measure, and calculus is involved in all of that stuff. Calculus consists of three concepts that you will be learning and then relearning through the course of Calc 1, 2, and 3. We're going to learn all three in Calc 1. You are going to explore one of them in Calc 2, and then you are going to relearn all three in Calc 3 in a 3D environment. So, calculus consists of the three topics: limits, derivatives, and integrals. And those are three separate worlds. They are all connected, but they all have its own its own chapters in a book. So limits, let me just give you that first. So this is going to be your chapter 2, it's going to be your chapter 3 and 4, and this is going to be your chapter 5, and that's your Calc 1. We have 4 chapters in Calc 1. Now you will have additional 2 chapters of integration in Calc 2, 6 and 7, and then in Calc 2 you are going to have 8 and 9, which are series, sequences, and power series. That's going to have a lot of limits. So technically you go back to chapter 2. And then Calc 3 takes all of this, recycles it, and puts it in a 3D environment. So now, limits. That's the topic of today. So after this introduction to calculus, we are going to talk about limits in detail. Limits are technically the fancy way to compute function value. So to find the y value of a function. You know how to do that in your pre-calculus course, right? You say f of x equals x squared. If x is 3, 3 squared is 9, you're done. That's it for limits. It's just on steroids. It's much more powerful. It will have a lot more features to it than just computing a single value, but in a nutshell, that's what it is. Y value of the function. Limits will provide the base for derivatives and integrals. So you will have some limit of f of x to talk about in chapter 2, and this limit will stay with you throughout the entire calculus, more or less used for definitions and so on. We can say x goes to a, but it can go to infinity as well. We'll see all of those features. Now, derivatives measure instantaneous change. Your speedometer on your car is actually derivative, live derivative. Derivative measures instantaneous change. You can measure average change, but if you want to have instantaneous change, that would be the derivative. They are very important. In business, you have something is called marginal cost. That's going to be the derivative. And obviously everywhere else in science and so on. So derivative measures change. Measures instantaneous change. And the notation for that would be the derivative of f of x, and as I said, those would be our chapters 3 and 4. Finally, we get to integrals, which are also known as antiderivatives. You are familiar that in life, certain things you can undo, and certain things you can't. So, you know, if you take off your sweater and you take it off as inverted sweater, you pull your sleeves out, you put it right side up, sure. So see, that's something that you can go back on. Certain functions have inverses, so you can calculate values back. So some of the derivatives can be undone, right? And you can go back into the original form, and you will do that with integrals. But some integrals cannot be solved. And that's going to be the tricky part. Not in this class, eventually. So when you're thinking about integration, you'll need to know that they undo derivatives because they're opposite. But then their integrals are going to calculate accumulation. They'll calculate sums. So their integrals are antiderivatives, and they are they calculate accumulation. Should I write accumulation or should I? Whatever. The notation is integral of f of x dx, and they undo derivatives. So that's your calculus. 3 topics. We cover all 3 of them in Calc 1. We cover all 3 of them again in Calc 3 in 3D environment. So all of your stuff with Calc 1 and most of Calc 2 is 2D. In order for us to survive calculus, we have to start with the notation and the notion of a function. Function is the most important thing of calculus 1. For instance, well, you've seen function in all 3 of these. So if you don't understand and don't know what the function is, you're done already, right? This is why we have to review these things and understand function very well. So function is a rule which assigns to each x in the domain a unique y in the range. This is the first time in this course that you are facing something that is called definition. It's very important to understand and learn definitions, because definitions tell you what the concepts are. This is a phone. And with the phone, you can make phone calls. No one does that, but you can, believe it or not. You can text, you can take pictures and videos, you can go online, you can play games. See, that's the definition of a phone. I used to be, you pick up the phone, you dial, right? I always avoided, like, I never had friends that had zeros and nines in their phone numbers because it was too long to, wait for the thing to come back, right? Today, you just text, you don't even talk. So now you have a phone, and we say the definition. This is a phone. You gave a name, right? Function is. So phone is a device which we can use to make phone calls, text messages, go online, play video games, take pictures, take videos, come up with other, right? You have the calendar, planner, all of that stuff in one device. So that's what the phone is. The theorem is how to use stuff. So definition is what it is, theorem is how to use it. So you want to learn how to do problems in calculus? You learn theorem. You know what the concept is? You learn the definition. And past that point, you don't need anything else, right? The problems will naturally work itself out. And I'll explain that as soon as we get the first lecture on derivatives, limits. So I define a phone by saying what you could do with it. And now you know what the phone is, and that's the definition. Now, the theorem is, how do you use the phone? Well, you have to unlock the phone first, right? So you unlock the phone. And when you unlock the phone, you use touch screen to access features. You see, that's the theorem. So now, imagine that you had no concept of the phone. For that, you would have to resurrect someone from 100 years ago, let's say. They have no concept of a phone, what it does, and they have no concept of a touch screen, no concept of apps, internet, games, none of that stuff exists. The theorem helps this person learn the way to use the phone. Because there are different types of phones out there. Smartphones. They have touch screen, right? So, Samsung phones, Android phones, right? And then they all have touch screen. The Apple garbage also has touch screen, which is produced by Samsung, right? So there you go. So it doesn't matter now. I don't have to tell you specifically how to use each individual phone. All I need to do is to give you the general theorem. Now, do you see the difference between learning theorems and definitions and learning the way you used to do algebra and why it doesn't work? Imagine this. I'm talking about the phone, and this is what algebra does. Picks up a particular model of a particular brand of phone, and you get to practice on it. And then you pick up a competitor phone, and you look at it, and you have no clue what to do. If you learned the definition, you would at least know that you're supposed to touch the screen for stuff to happen, right? So this is the difference between algebra and calculus. Calculus is telling you, don't learn to use a particular phone. Learn to use phone in general. And then, right, you learn that each phone goes online. Each phone has games. Each phone takes pictures, right? Each phone has touch screen. That's what the definition is. The theorem says use your finger to poke. You're ready to use any phone. Yeah, sure, this type of the phone will have apps this way, and the other phone will have apps the other way. You swipe down, you swipe left, you swipe up. Sure. 5 seconds of your finger going across because you have the concept, right? So this is why I am saying in calculus, when you are ready to do the homework and stuff, do not practice problems first. Learn the concepts first, and then it's a joke to apply those concepts to problems. We are learning what the function is. Types of the function. Polynomial, exponential, I'll list them all. Not all. The ones we use. There are 2,500 pages of functions that are out there. So, you learn the definition and learn the theorem, and then the rest is a joke. So, function is a rule. That's an important word. Which assigned to each x in a domain. Important word. Range, important word, and word unique, very important word. Let's go. Rule means formula. Is it e to the x, sine x, x squared? So that's what the rule stands for. What type of the formula you have? Domain, set of all input values, possible input values, range, set of all output values, and finally, unique. This is what makes function a function. So word unique, I'll write this in blood over here. One and only one y per x. If you take the word unique out, you change definition of a function to a definition of a relation. Is it possible for two runners to finish the race at the same time? The answer is yes, right? Is it possible for what I am writing right now to be displayed on my screen, on that projector, and online at the same time? The answer is yes. You see, all of these inputs, which is a single, the runners or what I'm writing, they have multiple y's. Those are not functions. We can't do calculus on those. But when you have a single input that provides single output, that's a function. It makes sense to talk about function of a switch. Just look. Now, when I push again, what's going to happen? What's going to happen when I push again? You don't have a concept of a light switch? Okay, let me show you. That's what happens. When I push again, what's going to happen? The light's off. Good. When I push again, what happens? Okay. The function of this switch is to uniquely control the set of lights which goes on and off. That's the function of the switch. See that? Uniquely. Do I have to worry about turning off lights in a hallway? No. How about my house? Okay, how about causing a major earthquake? Right? You see the purpose of a switch, right? So certain inputs will provide multiple outputs. The input that I'm providing with the pen on the screen is displayed on many different locations, not a function, right? You have X and you have multiple Y's, no bueno. But if I have a switch that uniquely controls one light, and that's it. Now, much closer example for you is texting. What happens when you push K on the keyboard? What prints on the screen? Yeah, imagine if there was no uniqueness. You push K, anything prints. Please write those scripts and install it for people. They're amazing. Push K, it prints R. You push backspace to erase that R, it prints M. You push backspace to delete M, it prints 2. It's amazing. All you need to do is to write a script that rewires the keyboard. That's infinite fun in offices. You write a little script, it rewrites the keyboard, and as you keep pushing any button, it randomly assigns. Typing a paper with that type of a keyboard is amazing. Like, you can't even imagine. Computer science guys will have a job, right? To figure that out. It was one of the nicer things I've done in the past. So, uniqueness is important. Otherwise, you would never be able to send a text message. You have to make sure that where the X and Y location of your touch on the touch screen is pressed, it prints appropriate letter that was displayed on that XY grid. So you provide the input, and your output is the letter that you were supposed to see. This is how important functions are. You buy something to assemble. Let's say you go to IKEA, right? You buy a piece of furniture. You want this nice shelf, right? Or whatever. You bring it home, you put it together, and you get a car. It makes no sense. Because the parts can only assemble one way, and that one way is the shelf that you hopefully purchased. Right? So you see that the functions play a crucial role in our everyday dealings. But also, as I mentioned with the screen and me writing, non-functions, relations, play a crucial role too. Because if you were not able to see what I'm writing, then I would have to chisel, right? Luckily, this non-function environment allows me to do stuff here, display it here so I can see it, display it there, and then also live as we go on. That's not a function. Single input has multiple outputs. So we can make diagrams. We can say input, which is domain, output, which is range, and if we have values 1, 2, 3, and values x, y, z, doesn't matter. If A maps to X, that's cool. If 2 maps to this one, is cool. If 3 maps this one, so this is all okay. Let's do that green. It's okay for 2 and 3 to map into Y because 2 has a Y as the answer. It doesn't have any other values as answer. And 3 has Y as the answer as well. The great example for this is x squared. What's 2 squared? That's a very difficult question, I understand. I will keep waiting until you come up with the answer. What's 2 squared? 4. I'm happy you warmed up those calculators. What's negative 2 squared? Also 4, right? So you see, if I am to square a 2 and square negative 2, they both provide 4. And x squared is a function. So that's okay. What's not okay? Where you go from the domain and branch into 2 different y values. That's no bueno. So, domain, range, 1, 2, 3, 1, 2, 3. So 1 goes into x, let's say, and then you have 2 go like that. Nope. So that's the visual representation. Now, here we have another visual representation of x coming in, function being applied to it, y comes out, which is, let's say, notation that y equals f of x, or f of x equals y. That's the notation. And you see your input here, which is domain, and you see your output there, which is range. So this is my notation. To understand physically what's happening, you take function f of x, let's say 3x minus 1, and the graph, the block diagram would be this: x, y, 3x minus 1. So what you do is you say, what is f of 5? Well, that's going to be 3 times 5 minus 1, which is 14. You are taking the 5 as x, you are feeding it into machine, and machine spits out 14. That's what functions do. Functions change numbers from one number to a different number. We're going to have in this class operators, guys. That's coming up. Operators are derivatives and integrals. They change functions. So this is your pre-calculus level, right, of function. Take a number in, do something with that number, spit the answer on the outside. It's a different number. We feed 5, 14 comes out. You feed in 10, 29 comes out on the other end. Calculus is going to take this on the next level up. It's going to take a function, put it in a machine, and a different function comes on the other end. We're going to shove x squared into the derivative, and the derivative is going to spit out 2x on the other end. You see that's a level higher. Because functions change numbers, operators, which are derivatives and integrals, will change functions. Cool? So now we first have to learn the basic of function in order for us to actually change functions. So functions change numbers. What types of functions are we going to deal with? All of those you learn in pre-calculus course. Polynomials, let's say p of x is equal to a0 plus a1x plus a2 plus x squared plus a3x cubed plus dot dot dot. So polynomial is covering a lot. You see, if you drop everything here, you are only left with p of x equals a. like y equals 3. Y equals 3 is a horizontal line, right? You learned that in algebra. That is your first polynomial. Horizontal lines are polynomials, cheapest ones. If you kill everything after the linear term, over here, you have your mx plus b, your linear lines. Those, the slanted ones, those are also polynomials. Kill everything after a square. You have your quadratic functions, x squared and so on. Cubic, 4th degree, 5th degree, and so on. So polynomials cover a lot. They cover constant functions, those are horizontal lines, linear functions, y equal mx plus b with a slope and y-intercept, quadratic, cubic, and everything else. Exponential functions. Those y equal, I'll put b to the x. Most of the time we'll deal with e to the x. So you're talking 2 to the x, 3 to the x, 5 to the x, and e to the x. Most frequently e to the x. Logarithmic functions. Y equals log base b of x. Radical. Y equals square root of a function, not just square root of x. Square root of sine x, square root of 1 over x, square root of ln x, all of them. No coughing. Next one is a rational function. That's when you take a function and divide it by another function. Let's use p and q. Both of these polynomials. You can put others, but that's fine. Trig functions. This is your pre-calc 2. And for trig functions, we have sine x, cosine x, tangent x, cosecant x, secant x, cotangent x. We have 6 of those. So these are our functions. And the next part we need to talk about is, and there will be a lot of this, absolute values and piecewise functions. We need to discuss those in greater detail because pre-calculus is not doing greatest job at those. So let's talk about absolute value. You learn in algebra. Well, let me ask, what is the absolute value? Come on, yes?
The distance of a number from 0.
Excellent. Yes. The absolute value is the distance of a number from a 0. Usually people go for it makes everything positive. No, that's a consequence, right? Absolute value is the distance of a number from 0. Its consequence is it makes everything positive. So, on the number line, there is a 0. There are numbers. I'll use positive and negative 5. So, absolute value of 5 is 5. Because if you are at 5, you have to make 5 hops to get to 0. So now I'm going to use actually red 5, and now I'm going to tell you that the black 5 and the red 5 are not the same 5. And you're going to go, what? 5 is not 5? Exactly. 5 is not 5. Now, what do I mean 5 is not 5? Well, we assign units and things to numbers. Let's call that, perfect, 11:30. Let's say 11. Just think of 11. Now I pointed my finger towards the clock. You immediately thought 11 o'clock, right? Did you? Because I just said 11. And more than half of you looked over there, and your concept in the head was 11 o'clock. You know what I was thinking about? 11-year-old. I pointed to the clock, but I was thinking of the 11. So you see that 11? 11 years old, 11 o'clock. They both have 11, but they're much different concepts, right? Vastly different concepts. So, this 5 is a location. You know your car is parked on a parking lot? That's a location. You're sitting in your particular seat. That's a location. This is how far you are from the door if you need to run, right? So, you have the black 5 is a location. That's your spot. The red 5 is the distance you have to cover to get out. Right? The other 5 has the same deal. Black, -5, is a location. Where your car is, where you are. And then there will be another 5 hops. And that is going to be the distance. And that is all again going to be positive value. So I'm going to have these 5 hops. And I'm going to have another red 5. And I'm going to say that absolute value of -5 is, again, a red 5. And in this sense, black 5 and the red 5 are not the same. One shows location, the other one shows the distance. And all the different concepts. But now, if we are to just look at this and disregard the theory of distance, location, and all of the physics that is associated with it, it clearly says, oh yeah, absolute value makes everything positive. Now, I want to apply that to functions. If I put absolute value on a function, that means that all of the answers that I get, all of the y values, better be positive numbers all the time. Now, you probably all memorized the graph of absolute value of x as what? What was it? Absolute value of x. Just a v at 45 degrees. Great. And now, as every good 5-year-old, I go, why? I try to hit that tone. Why? Why is it v at 45 degrees? See? Now, this is where understanding comes in. There is a difference between you being told something and learning it, and memorizing it, sorry, or you actually sitting down and learning. What if I asked you, draw absolute value of sine x? Because that's the one we need. Draw absolute value of ln x. That's the one we need. You see the problem between algebra and calculus? You memorize the particular example, and this becomes the entire reality of absolute value. The first time I ask you for absolute value is going to look like this. Now what? Right? So let's not memorize this. Let's figure out what it is, how we get it, and then you can apply the same principle to any graph anyone puts down. So we say absolute value of x. Okay, that means y equals x, and that is 45-degree line. Absolute values on the y-axis do not like any of the negative stuff, so I better bump that one up using x-axis as a mirror. Hello, absolute x graph. Now I'm going to use the same principle for sine y equal absolute sine x. I start with y is sine x. Okay, that's there we go. Ends at 2 pi for the principal period. Oh, absolute value doesn't like negative y's, so that's out. There's the bump on top. So that's the graph for absolute sine x. So you start with a graph without absolute value, and anything that is in the negative side gets mirrored up. So the bump that was on the negative side of the y gets bumped up. And you just get these two bumps now for absolute sine x. Great. Now it's time for you to draw absolute value of ln x. Go ahead. Draw absolute value of ln x. You know what ln x looks like. If you don't know, you'll have to cheat. You have to find it online, you'll have to find it, right? You are supposed to know basic graphs, right? ln is basic one. All of the functions that I listed up there, you need to know what their basic graph looks like, because we'll be upgrading all of those. If you have issues with that stuff, see me so we can clear that up as soon as possible. That's your pre-calc 1 and 2. So what is the graph of absolute value of ln x? Okay, so goal is to find absolute value of ln x. What we know is y equals ln x. Y equals ln x goes through 1 like that. So we take the negative part and we bump it up. So it has a spike at 1. So the graph goes whoop, and then like that. That's what absolute value looks like. Do you remember this? Do you memorize it? No, never. You are supposed to memorize and remember basic graphs, basic sine x, basic ln x, basic e to the x. And then when you need to do something with them, you just say, okay, absolute value, can't have anything below x-axis, bump it up. So it doesn't matter anymore, right, what the actual graph looks like. You can derive it quickly. So one more time, that's the difference between algebra and calculus. In algebra, you are supposed to practice this graph, okay, V, 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 until you bleed under your fingernails, right? And then you show up for the next class, and I say, okay, time for absolute S, and you go bump, 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 right, until you bleed again under your fingernails. And then you show up next class, and you see, memorize, memorize, memorize. You memorize example by example, case by case. Yes, that's the way to learn algebra. Sure. Is there a way to learn calculus? No. If there are 1,000 different functions, and this is a drop in a sea, are you going to sit there and memorize 1,000 absolute value graphs? No. So this is the way to go. You are learning a concept, and then you remember the concept only, and you apply that concept. So you will practice the concept. This is why it's a bad idea to go home and do homework. What do? You go home, you learn the concept, then homework is a joke and used to practice your skills. So this is why I say for homework, someone is going to do it properly. You learn the concept, 5 examples is enough. Some of you will do 30 examples trying to memorize each particular type of the question, and then come to the test and probably see a question you've never seen before, because it's just a different function. Those who know the concept, a joke, and those who never seen it said you will never taught a problem like this. It's impossible to teach in calculus every type of a problem, because you're supposed to learn concepts, not problems. And that's the difference between your previous and education now. So that's our absolute value. The last part on this is piecewise function. Pieces, right? Multiple parts. F of x is equal to 3x plus 1 and negative x squared for x's less than 5, for x's in between, negative 5, negative 5 and 0, and for x is bigger than 0. We are going to have a lot of functions that look like this in calculus. Before you run away, please realize that these are just 3 functions stitched together. They are not on top of each other. They are side by side. Function, which is a constant function 3, just a flat line. You've seen that on movies. Right before they go through. that function, that's useful for you. This function is only in effect up to -5. So what do? You draw the long x-axis, and you can put a barrier at -5, and then this function is in effect until that barrier. You have a y equals x plus 1 linear function in effect between -5 and 0, and you have negative x squared in effect after 0. So that's as simple as it is. Each function is a separate function which is in effect in a different partition of the graph. So to graph this, you draw your x and y coordinate system. And now we go -5. This is not an asymptote, so I'm gonna draw it orange. This is a barrier. And then I have another barrier at the y-axis because x equals 0. So I get to draw 3 with the open circle at -5 because that's my first graph. I'll put a black dot there. The next portion I'm going to draw in red. Function x plus 1. Well, we know that's a 45-degree line which goes through y-intercept 1. So it's supposed to go through 1, and it's supposed to be 45-degree line, so it's supposed to be this forever, right? But remember, it is supposed to be only between -5 and 0, so I have to erase the extra stuff, which is this. And I am only allowed to have this between -5 and 5. It goes through 1 over here and -1 over here. And I have closed dots on each end because of the equal signs in inequalities, right? It's less equal than, so I have the closed dots. And that's my red part. And now we go light blue. For -x squared starts at open circle and goes -x squared there. Piecewise function. 1, 2, 3 lines, 3 pieces, 1, 2, 3 regions, 3 pieces. Each piece you get to draw in its own area. Now, if you're using pencil, you can draw full functions and then erase them in areas where they don't belong, like I did with the red. You saw me with red draw the line all the way. But the red function has to stop at x equals 0, which is y-axis. Because the red function stops at 0, and at 0, the x squared, -x squared, begins. So there it is, begins. No equal sign, open circles, equal signs, closed circles, filled in. We are going to use this a lot in our limits, obviously, but it's going to show up later. Taxes are coming up, right? The tax brackets, this kind of graph. It's called a step function. It's a piecewise function where each of your tax brackets, we can just sketch the tax bracket graph, but that's one of the applications of these piecewise functions. So if you go to the tax website, they tell you that you pay 10% tax if you make 0 to, I don't know, $10,000. You pay 15% tax if you make between $10,000 and, I'm making numbers up, $25,000. You pay 25% tax if you go from $25,000 to 90. I don't know. We can go and look. You just type in tax brackets. These are, you know what? I'm going to type tax brackets and we're going to see the actual numbers because why not? Tax brackets. So as you type in tax brackets, you're going to come up with 2018 rates because you are filling taxes for the last year, 2018. Well, I was close. I said up to 10,000. It's actually 9.5. I was off on the 25K because that's apparently 40 almost. So let's keep that at 10. We're going to change this to 40K. 40K to 82K. So I'm just going to call that 80 because lazy. Oh, the rates are now changed too. This is 12. This is 22. 24. Between 80K and 160, whatever. That's enough. And 3 dots as we go on. Note the jump of 10%. This is where the middle class is done in the United States. Look at that. 2% jump, 10% jump for the most people jumping, and then 2%, and then another big one after 150 of 8%. But most of the people, because these are the people that get 50 cents raise and a dollar, most of them, right? Because if you have a raise that little, it just bumps you over 38,000. Because what's the $38,000? Divide it by 12 months, divide it, right? See what the monthly payment. So most of the people make that money, and if you don't do donations and things, right, the tax bracket stays there, and so you get a dollar raise, right? You say, okay, now I make more money, but you actually lose, $4,000 or $5,000 over that raise because it's jumping the tax bracket. Anyway, so to quickly graph this, we have our function. These are my x values, which is money, and this is my y, which is percent. So each one of these will have, let's go with 10%, 20%, 30, these are percents. And this is what money is. So we have our 0, 10, 20, 30, 40, 50, 60, 70, 80 is important. 40 was important. 20 was not important. 90, 100, 110, 20, 30, 40, 60, 160. There we go. So to graph this quickly, 10% will go here. Then we have a 12% going up to 40. Then we have 40 to 80 at 22%, so that's going to start at 22%, go to 80. At 24%, which is right here, goes to 160, and so on. There you go. It's a piecewise function. It's also known as a step function because it looks like steps, like stairs, right? It's called a step function, but it's a piecewise function. And that's your application of these functions immediately because the texts are coming up, so you can see that. So that's the story of functions. Functions change numbers. You plug in x value, it gives you y on the other end. That y value is the output. We use this concept all the time to calculate prices, to calculate pretty much everything we have. The function could stop being a function if a single input produces more than one output. We generally, well, we can't use those in our STEM because you can't have a different outcome. Right? Science likes certain outcome. When you plug something in, you know what's happening on the other end. You can predict the value, you know what the value is. So for sciences, we like functions because functions give us exactly the output and there is no debate on whether one or the other outcome is going to show up and so on. So that's why function is so important. Calculus, as you've seen, is only done on functions. So your function, you have a limit of a function, you have a derivative of a function, you have integral of a function. If you don't have a function, you can't integrate. Derivatives will have a method we'll learn. It's called implicit differentiation. So it still works, but it's annoying. And limits are done as integrals exclusively on functions. So we'll deal with that. The next lecture is introductory lecture to limits. So see you after the break. Bye.